In this video, we want to talk about a sampling distribution for a proportion. Now, if you think about everything we've looked at so far, we have gone from our parent distribution, which is X, and then we've done our sampling distribution, which is an X bar, right? Now we want to go to use a different statistic, right? We talked about X bar being a statistic. We now want to look at a proportion sampling distribution. So to give you an example, and once again, if I was in class and we had time to do this, we could look at this experiment, which I've done in the past, which imagine I gave everybody a penny. And I asked you to spin the penny, not flip it, but spin the penny. So you'd spin it on its side, and then once it would fall over, you would get heads or tails. Now, this does not work out to be as close to 50-50 as flipping a penny, so we don't know what the proportion is. So we're going to do a whole bunch of samples to create a sampling distribution for maybe the population that we don't know. So I've done this in the past. So we have each person spins the head 50 times, spins a coin, and records the number of heads. So here are the answers that this class got. And you can see the top is the number of heads. If we convert this into a percentage, so this number down below would be our p hat. Remember, that is the proportion statistic that we get. Okay. I will mention one time we had this, somebody actually got their penny to stay on its side. It just spun in circles and then stayed right on the edge and didn't fall heads or tails. So that is possible. So here is one class's results. Here is another class's results. Okay, their average was 56. Here's another class's results. So you can see I've done this. Here's another class's results. I've done this for many years. And you get numbers that are a little bit above 50. Okay, it's a little bit more likely to fall on heads from our experience. There's another one, and so forth. So now really what you're doing is you're deciding heads or tails. This is really a binomial distribution. This is a discrete distribution. When you look at this, nobody wrote down that they got, 27.4 heads. They're all whole numbers. They're all discrete. So let's say we want to spin a coin 20 times, and let's say our probability of getting a heads is 0.55. What's the probability you get exactly 14? Well, we could do this back on our calculator. If you remember, we did binomial, and we said if we did 20 trials and the probability of success was 0.15, what's the probability of 14? And we could get our answer. That works. Now, what happens if we said 50 times and you get exactly 24? We could also do that as an exact value. But let's say we want to look at something beyond just a set value. Let's say we look at this. Let's say we do 20 times, and let's change this to 0.55. And here is our distribution of all the things you could expect to happen. So if we go back to here, let's go back to our 20. What did we get as our, for 14 heads, we got 0.07. So if I look at 14, there is our 0.07. Or you get 13, or all of these. So if you're finding an individual value, we can do that. But let's say we want to find between 8 and 14. Now we have to add all these up. So one of the things we're going to do is we're going to look at a way to approximate, skip through all this, we're going to look a way to approximate our normal distribution, our binomial distribution, with the normal curve. And you can kind of see this graph kind of looks like a normal curve. So if I would change this, let's say to 50, and we get that, and I click normal, approximate normal, you can see this graph is approximately normal. So we are able to use our normal distribution and use our normal CDF to answer this. So let's talk about some notation things here. First off, our sampling proportion, what we get from our sample is p hat, and that is your number of successes over your total number. And remember, n is your number of successes, your number of trials. R, or sometimes we use X, is our number of successes. P is our probability. Q is 1 minus P. Now, in order to approximate this binomial distribution as a normal distribution, we need a couple things to be true. First off, this NP and NQ has to be greater than 5. If that's not the case, you cannot do this. And also, we still have our thing from before, too, that N has to be greater than 30, since we don't know anything about the original. And what that means is if your probability is really, really small or really, really high, it's going to throw off being able to approximate it with normal. And you can see this if I switch back to over here. If I sample size is 20 and I click approximate normal, you can see I get an error. To use a normal approximation, n must be greater than 30, and MP has to be greater than 5, and n 1 minus P, or Q, has to be greater than 5. That may be hard to see on the video right now, but that's the case. We have to do that. Now, when I put in 50, which I intentionally did, and click normal, now we have a large enough sample size, NP, NQ is bigger than 50, and we're going to be able to approximate it with normal. Now, to approximate it with normal, we need to find our approximation, our mean and standard deviation. So what we're going to have is our mean of our p hat distribution is just equal to p, and our sigma p hat distribution is equal to the square root of pq over n. Now, if we go back to here, though, you can see we have a problem. There's gaps, because the binomial distribution is discrete. So there's gaps. It's not continuous. So in order to make this work, we're going to have to convert to continuous distribution. And we're going to have to use this as called a continuity correction. And I skipped over it, but let me go back to it. Same thing, standard error is still the standard deviation of this p hat distribution, just like it was our sigma x bar distribution before. All right, so here's how we're going to make our continuity correction. We're going to correct from a discrete to continuous random variable. What we're going to do is we're going to add and subtract this 0.5 divided by n. Okay. Now, when it says add and subtract to the right or left endpoint, the goal is always to make our numbers bigger. So if you have two numbers, here and here, we want to make it bigger. So we're going to subtract from the left endpoint to go here. We're going to add to the right endpoint to go here. We want to make it bigger. What am I talking about? Let's do an example. For n equals 20, and we have, what's the probability that p hat, so if we take a sample of 20, what's the probability that our sample percentage will be between 0.54 and 0.86? Now what we want to do is we want to convert this to an X distribution, our normal distribution, so we can put it into normal CDF and find our probability. So the first thing we have to do is find our continuity correction, which is 0.5 over 20, which is 0.025. And then we subtract that from our left endpoint, which would give us 515. and we add that to our right endpoint, which gives us 0.885. So this would be what we're trying to find. Now, I'm not going to go through with that yet and find the standard deviation and the mean. We are just doing the continuity correction here first before we go to the next step. So let's have you try this one. So your n is 40, and you want to find what's the probability that p hat is between 0.72 or 0.31 and 0.72, and then we want to convert this to an x. So if you want to pause the video here for a second and try this one, and then we will come back. All right, so now that we're back, first thing is we've got to find our continuity correction, which is 0.5 divided by 40, which is 0.0125. So we have to subtract this from 0.31, which is 0.2975, and we have to add this to 0.72, which is 0.73.25. And now we've converted this from binomial discrete distribution to a continuous distribution. So let's look at an example. Suppose 12% of the population are in favor of a new park. So that is our P is 0.12. We're going to survey 200 citizens. There is our N. What is the probability between 10 and 15% of them will be in favor of the new park? So we have, what's the probability that our P hat is between 10 and 15? And where we're eventually going with this is if we get a probability here that will let us know, does this percentage seem correct? If our probability is super, super small, that there's no chance it's in here, then that makes us think, maybe that value may not be absolutely correct. So, all right, first thing, we have to subtract from here. We need to add from here. So that gives us 0.0975x to 0.1525. But the next thing we have to do is we need to find our mean and our sigma to put this into our normal CDF. Well, our mean is just 0.12. Our sigma, if you remember, is PQ over N. So let me rewrite that here. This is just P, and this is PQ over N. And the value I get here is 0.022978. So now we've done our continuity correction. We've found our new mean and standard deviation. So now we can go to normal CDF, and we now have it converted to a normal distribution. We can put that in, and we can get 0.7576. So if 12% of people favor the new park and we survey 200, we have a 75.76% chance that we will get between 10 and 15% of them that say they favor the park. So another example. A recent study found that 86% of kids believe in Santa Claus. If 50 kids are asked if they believe in Santa Claus, what's the probability between 80 and 91% say they believe? So we have 0.8, p hat is 0.91. The first thing we need to do is we need to convert this to a normal distribution, to just x. We do that by finding our continuity correction, which is 0.5 over 50, which is 0.01. We subtract that from the 0.8, which is 0.79. We add that to the 0.91, which is 0.92. My mean p hat is 0.86. My standard deviation of p hat is the square root of 0.86, 0.14 over 50. We should get that. We then put this into normal PDF, 0.79, 0.92, 0.86, 0.0491, and we get 0.0491. So you notice when we're doing this for our proportion sampling distribution, we divide by n to get our sigma right here. So we only have one way to do this. This is always with the sample. It's not like with the central limit theorem where you had to decide, is it 1 or do I divide by the square root of n? When we're dealing with proportion, we are always using this formula for our standard deviation of our sampling distribution. All right, you're now able to do the homework on 5.5, the sampling distribution of a proportion.